Hello everyone, welcome to SleepSpace. Tonight, we will talk about something truly vast and deeply mysterious. How many multiverses are there? Settle in, get comfortable, and let your mind drift gently as we explore the science and imagination surrounding the idea of infinite realities. The idea of a multiverse, that our universe might be just one of many, has long fascinated physicists, philosophers, and storytellers alike. For most of history, we believed the cosmos consisted of only what we could see: Earth, the stars, and the void beyond. But as science advanced, so did our sense of scale. First, we realized Earth was just one planet among many. Then, that our sun was one star in a galaxy of billions. And then, that our galaxy was just one among potentially trillions. It seems every time we think we've reached the edge, a new horizon opens. So what if our universe itself is not the only one? That's the essence of the multiverse concept. But to ask how many multiverses there are, we first need to ask, what exactly is a universe? In physics, a universe is everything that exists within a given region of space and time. Our observable universe stretches roughly 93 billion light years across. But even that is just what we can see. Beyond that, the universe likely continues, and it may never end. Still, even this vast expanse might be only a single bubble in a far larger reality. There are several types of multiverse theories proposed in science. Some arise from cosmology, others from quantum mechanics, and others from the mathematics of string theory. Each theory gives us a different view of what a multiverse might be and how many universes might exist. Let's begin with the cosmic inflation multiverse. In the 1980s, physicists proposed that in the first fraction of a second after the Big Bang, our universe underwent a rapid expansion called inflation. This idea helped explain why the universe looks so uniform today. But inflation theory also leads to a strange possibility. If inflation can happen once, it might happen over and over, endlessly. This leads to what's called eternal inflation. In this scenario, our universe is just one bubble among countless others. Each bubble universe forms in its own region of space, isolated from the rest. These bubbles may have different physical laws, different particles, even different dimensions. In this model, the multiverse is infinite, and so is the number of universes. Now consider the quantum multiverse, which arises from the rules of quantum mechanics. At the smallest scales, particles don't have definite positions or speeds until they're measured. Instead, they exist in a cloud of probabilities. This idea is at the heart of the many worlds interpretation of quantum mechanics. Proposed in 1957 by Hugh Everett III, this interpretation suggests that every time a quantum event occurs, like an electron choosing to go left or right, the universe splits. One version continues with the electron going left, another with it going right, and so on for every quantum event in the universe. According to this view, there are an unimaginable number of parallel universes, each representing different outcomes of every decision, every particle interaction, every possibility. This creates a multiverse of branching timelines, an endlessly growing tree of alternate realities. Then there's the brain multiverse, which comes from string theory. String theory proposes that all particles are actually tiny vibrating strings. These strings may exist in more than 3 dimensions, perhaps 10 or 11 in total. If our universe is a 3-dimensional brain, short for membrane, floating in a higher dimensional space, there may be other brains, other universes, floating nearby. Sometimes these brains might even collide, causing events like the Big Bang. In this theory, the multiverse is a sea of universes, each brain like a sheet of paper drifting in a cosmic ocean. Some might be nearly identical to ours, others radically different. There's also the mathematical multiverse, proposed by Max Tegmark. He suggests that all structures that can exist mathematically also exist physically. In other words, if a universe can be described by a consistent set of mathematical rules, it exists somewhere. According to this view, there are not just trillions or quadrillions of universes, but literally every mathematically possible universe exists. It's a bold idea and difficult to test, but it stretches our imagination to the very limits. So, given all these theories, how many multiverses are there? It depends on which framework you believe. In the inflationary model, the number is infinite. In the quantum model, every decision splits reality into more branches, also infinite. In the brain world, there might be a large but countable number. In the mathematical model, the number is, well, beyond comprehension. But perhaps the more interesting question is, are these universes truly separate from ours, or are they somehow connected? Some theories suggest that gravity might leak between brain worlds. Others wonder if black holes are portals to other universes. Still others speculate that quantum entanglement hints at a hidden connection between realities. These ideas are deeply speculative, but they reveal something important. Even the most far-out scientific theories are rooted in an attempt to understand the world we live in. They arise not from wild guesses, but from serious attempts to explain the data we observe. Multiverse theories also have implications for the nature of life and consciousness. If there are infinite universes, then there might be versions of you living very different lives. Perhaps some that are nearly identical, others vastly different. In one, you may have chosen a different career. In another, you may never have existed at all. This can be a disorienting idea, but also a comforting one. The multiverse may mean that no possibility is ever truly lost. Somewhere, every version of you continues. Still, it's important to ask, can we ever test these ideas? That's one of the biggest challenges with the multiverse. By definition, these other universes are not part of our own. We can't see them, measure them, or interact with them. At least not yet. Some scientists argue that if a theory cannot be tested, it shouldn't be considered scientific. Others reply that theories like eternal inflation make predictions we can check, such as patterns in the cosmic microwave background, and that the multiverse is a logical consequence of those theories. The debate continues. In the meantime, physicists continue to refine these ideas. Observatories search for clues in the sky. Particle accelerators probe the fabric of reality. And computers simulate entire universes, exploring what might be possible. The answers remain elusive, but the journey continues. So how many multiverses are there? It may be that the number is truly infinite. It may be that there is just one universe and we are imagining the rest. Or it may be that reality is far stranger than we can yet understand. But what's certain is this. Asking the question opens a door to something vast and profound. It invites us to think bigger, to wonder more deeply, and to embrace the mystery of existence. As we explore the multiverse together tonight, let yourself relax into the wonder of possibility. Drift gently through the space between thoughts, between stars, between realities. We are only beginning to understand how vast the cosmos truly is. And that is just the beginning. To explore how many multiverses might exist, we need to look more closely at how each theory imagines them being born. One of the key distinctions among multiverse models is whether new universes are created simultaneously, successively, or endlessly, and what mechanism causes them to emerge. Let's return to the idea of eternal inflation. In this theory, space is expanding continuously, not just in our universe, but in an overarching multiverse space. You can picture this as a vast, inflating loaf of bread. Every so often, a bubble forms in the loaf, a pocket of space where inflation stops and a universe like ours begins. But inflation doesn't stop everywhere. It keeps going in other regions, spawning more and more bubbles. This is called a false vacuum decay, where a high energy state of space transitions to a lower energy state in isolated regions. When this happens, that region becomes a universe. This process is thought to be random, chaotic, and eternal, meaning it never ends. So the number of universes grows forever, like popcorn kernels popping endlessly in an infinite pan. But what's truly fascinating is that each bubble universe may follow its own version of physics. The constants we take for granted, like the strength of gravity, the speed of light, or the mass of the electron, may differ from bubble to bubble. In some universes, stars might never form. In others, atoms might not be stable. Most of these universes might be lifeless, but a few, just like ours, might be suited for life. This gives rise to what's called the anthropic principle, the idea that we observe this particular universe because it's one in which observers like us can exist. Now, let's turn back to the quantum multiverse, the one predicted by the many worlds interpretation. This model doesn't require bubbles forming in space. Instead, it's about branching, a splitting of reality itself. Whenever a quantum event occurs with multiple possible outcomes, all of them happen in separate, non-interacting branches of the universe. Let's take a simple example. Suppose a radioactive atom has a 50% chance of decaying in the next minute. In the many worlds view, both outcomes occur. One universe where it decays, one where it doesn't. If you're standing nearby, you split along with the atom. In one world, you witness the decay. In the other, you don't. This kind of branching happens constantly, everywhere, all the time. Every photon, every electron, every molecule is undergoing quantum interactions that might lead to different outcomes. So instead of a universe bubbling into being from a vast inflating space, we have a universe that splits again and again, like a tree endlessly growing new branches. The number of universes doesn't just increase, it increases exponentially, branching every moment. It's a dizzying concept, but it has a strange elegance to it. Rather than needing mysterious new physics, the many worlds theory takes the mathematics of quantum mechanics at face value. It says, don't collapse the wave function. Just accept that all possible outcomes happen, each in its own world. The question, of course, is whether these quantum branches are real in the physical sense, or just a mathematical tool. Some physicists argue that these alternate worlds are just part of a useful formalism, not truly existing in any tangible way. Others believe they're as real as our own, but forever beyond our reach, because we can't interact with them once they branch. Interestingly, quantum mechanics also introduces something called decoherence, the process by which quantum systems become entangled with their environment and lose their quantum weirdness. Decoherence prevents the different branches from interfering with each other, locking them into their own separate histories. That's why, in practice, we don't observe other versions of reality overlapping with our own. But according to the many worlds view, they're still out there, as real and full as this one. Now, let's consider another perspective, the cyclical universe. This idea suggests that universes don't just pop into existence and expand forever. Instead, they may follow a cycle. A universe could begin with a big bang, expand, and then contract in a big crunch. only to be reborn in a new Big Bang. Over time, this cycle might repeat endlessly, giving rise to an infinite number of sequential universes. Each cycle could bring different conditions. Some models say that tiny quantum differences at the start of each cycle would lead to slightly different outcomes, and over many cycles, vastly different universes. This is a more ancient vision of the cosmos, echoing ideas from ancient philosophy. Time as an endless wheel rather than a one-way arrow. A variation of this is found in the ekpyrotic model related to string theory. Here, two branes, higher dimensional universes, collide periodically in a higher dimensional space. Each collision sparks a new Big Bang, birthing a new universe. These universes may exist in parallel, or one after the other, in an unending cosmic dance. So far, we've covered eternal inflation, many worlds quantum branching, brane collisions, and cyclical rebirths. Each one offers its own vision of a multiverse. Some suggest spatial separation, others temporal cycles, and still others infinite splitting of realities. But what ties them all together is a shared message. Our universe may not be alone, and if these models are even partially correct, the number of universes could be limitless, literally uncountable. That brings us to a key philosophical and scientific dilemma. Can infinity truly exist in nature? Mathematically, we use infinity all the time. It appears in calculus, geometry, and in theories of space and time. But in the physical world, infinity is harder to pin down. Is the universe truly infinite in size? Or is it just unimaginably vast? Can there be an infinite number of particles, or events, or timelines? Or are we dealing with large but finite quantities? If we accept that the multiverse contains an infinite number of universes, we run into strange consequences. For example, in an infinite multiverse, there are infinitely many exact copies of you, and infinitely many nearly identical versions. In some, you made different life choices. In others, you speak different languages. In still others, everything is the same up to this very moment, except one atom is shifted slightly. This leads to a philosophical puzzle called the measure problem. In an infinite multiverse, how do we make predictions? If everything happens somewhere, how do we define what's likely or meaningful? Scientists and philosophers are still trying to make sense of these questions. And yet, the multiverse is not just theoretical. Some versions of it are serious consequences of otherwise well-established theories. Inflation, quantum mechanics, string theory all suggest, in some form, that we may be part of something bigger. That said, not all scientists agree. Some argue that the multiverse is unscientific because it may never be directly tested. Others believe it's a natural extension of our theories and may one day be observable, perhaps through subtle patterns in the cosmic background or unexpected behavior in particle collisions. Whether or not the multiverse is real, one thing is certain. The more we learn about the universe, the more mysterious it becomes. Every discovery opens new doors, and behind some of them may lie entire other worlds. Tonight, as we let our minds drift through these possibilities, it's worth reflecting on how recent these ideas truly are. Just 100 years ago, we didn't know galaxies existed beyond our own. Now, we talk seriously about multiple realities, higher dimensions, and quantum branches. Science has expanded our perspective in breathtaking ways, and the journey is far from over. So, as we continue to explore this question, how many multiverses are there? Remember, even if the answer is too many to count, the act of asking changes how we see everything. It invites us to let go of boundaries, to imagine more deeply, and to glimpse, if only for a moment, the true scale of reality. As we continue our journey through the multiverse, let's focus on one of the most curious questions yet. If there are other universes, is there any way to detect them? Could we find signs, even the faintest hints, that we are not alone in this cosmic sea of possibilities? To answer that, we need to revisit the notion of cosmic isolation. According to most multiverse models, each universe is separated by an immense gap, not just in space, but in causality. That means nothing from one universe can reach another, at least not through ordinary means. But some researchers have speculated that if other universes came close to ours in the distant past, or collided with us during formation, they might leave scars, subtle imprints in the structure of space itself. One place scientists have looked is in the cosmic microwave background, the afterglow of the Big Bang. This faint radiation fills all of space, and it's like a baby photo of our universe. It carries information about the earliest moments of time. Some researchers have analysed the CMB data looking for unusual patterns, cold spots, concentric rings, or areas of statistical imbalance that might suggest a collision with another universe. To date, no definitive evidence has been found, but the search is ongoing and more sensitive measurements are being made every year. Projects like the Planck satellite and upcoming space telescopes are sharpening our view of the early cosmos. If we ever do find an anomaly that can't be explained by known physics, it may point to a brush with another universe long ago. But what about quantum multiverses? The kind that branch off with every possibility. By design, these are completely non-interacting. Once a branch splits, it evolves independently. There's no way to hop from one to another. You can't talk to your alternate self or peek through a dimensional window. Decoherence seals the deal. Each universe is locked off from the others, even though they all unfold side by side in a vast and branching structure. Some scientists and philosophers have wondered whether consciousness plays a role here. Could our awareness somehow experience multiple realities? This leads into deeply speculative territory, but it's a natural question to ask when exploring the many worlds interpretation. After all, if every version of you continues to exist, why do you only feel like you're in this one? One possibility is that the continuity of memory and identity keeps your conscious experience bound to a single branch. In other words, you don't feel the split because your awareness follows just one thread of the many. Another idea, much more controversial, is that consciousness itself might be non-local, that it might tap into structures beyond the ordinary dimensions of space and time. These ideas remain speculative, but they highlight an important point. As we consider the multiverse, we are also forced to reconsider what it means to exist, to choose, and to be aware. Now, let's shift our focus to string theory and the multiverse it implies. String theory suggests that all particles are actually tiny vibrating strings, and the type of vibration determines the particle's properties. To make the math work, string theory requires more than the familiar 4 dimensions. It needs 10 or 11. Most of these extra dimensions are thought to be curled up, so tightly that we can't detect them directly. But the way these dimensions curl up matters deeply. There are countless ways the extra dimensions can compactify, and each configuration leads to a different set of physical laws. One compactification might lead to a universe with electrons and protons. Another might have no stable matter at all. Another might have different forces, particles, or even no chemistry. The number of possible compactifications is enormous, often quoted as around 10 of 500. That's a 1 followed by 500 zeros, a number so vast it defies comprehension. If each configuration gives rise to a different universe, that would mean an inconceivably large multiverse, each version with its own set of rules. its own stars and atoms and possibilities. This is sometimes called the landscape multiverse, and it raises some interesting questions. If so many universes are possible, why do we live in this one? Why do the physical laws here allow for galaxies, life, and thought? One answer is the anthropic principle, which we briefly touched on before. It says, we find ourselves in a universe that allows life, because only such a universe can contain observers. It may not be surprising that we live in a life-permitting universe. It may be that all other universes are lifeless and unobserved. Some scientists find this explanation unsatisfying. It feels circular or even like giving up. But others argue it's a logical consequence of the multiverse idea. If countless universes exist, we should expect to find ourselves in the kind where existence is possible. It doesn't explain why the multiverse exists in the first place, but it does help explain why our universe looks the way it does. Let's take a step back and think about just how varied these other universes might be. In some multiverse models, the laws of physics are nearly identical to ours, with only slight changes in constants or particles. These universes might look and feel familiar. In others, the differences could be radical. Universes with 5 spatial dimensions, or no time, or alternate forms of logic. Some may lack gravity. Others might have never formed stars. Others still might exist as pure mathematics or as formless potential. The deeper we go into multiverse theory, the more we blur the line between physics and metaphysics. We are no longer just studying what we can observe. We are trying to infer what might exist beyond observation, based on the mathematical frameworks that describe our universe. This is both a scientific and a philosophical adventure. It challenges our assumptions about reality. It asks, is there a fundamental universe, or are there only possibilities? Is reality something fixed or something emergent from deeper patterns? In that sense, the multiverse invites us to be humble. It reminds us that what we know may be a tiny island in an unfathomable sea. Even if we can't reach the other universes, even if they remain forever inaccessible, the very idea of them shapes how we think. And while we often picture the multiverse in terms of copies of our world, alternate Earths, alternate lives, the truth is likely much stranger. The vast majority of universes, if they exist, are not like ours at all. They are not parallel in the familiar sense. They are divergent in every possible way. They may be completely alien, even unrecognizable. So far, we've considered inflationary universes, quantum branches, brain collisions, cyclical models, and string theory landscapes. All suggest that reality may be layered, plural, and infinite. But none can yet give us a definitive number. Whether it's 10 or 500, or uncountable, or simply more than one, depends on which theory turns out to be true, if any. And that raises a final point for tonight. What if the multiverse is not real? It's possible that these ideas, however elegant, are only mathematical artifacts, reflections of our models, not of reality. In that case, our universe may truly be unique. That idea is just as profound in its own way. To live in a one-of-a-kind universe, a singular cosmic expression, is no less mysterious than to live in one among trillions. But even if the multiverse is never proven, the questions it raises push science forward. It stretches our models. It forces us to consider what's possible, and it may lead to discoveries we never would have made otherwise. As we drift through this topic, let the enormity of it sink in, not as something to fear, but as something to marvel at. The idea that there might be more than we can see, more than we can touch or measure, is a quiet invitation to wonder. And that is a beautiful thing. Let's pause for a moment and reflect on just how revolutionary the multiverse idea really is. For most of human history, we assumed that reality consisted of what we could see, touch, and measure. The stars overhead were thought to be fixed in a crystal sphere. The universe was assumed to be eternal, and Earth was its center. Bit by bit, science peeled away these assumptions. We learned that Earth is one planet among many, that the Sun is just another star, that the Milky Way is only one galaxy in a vast swarm. Each time, the cosmos grew larger, and we grew more humbled. Now, the multiverse idea takes this expansion to its ultimate conclusion. Not only is the universe not the center of all the things, it may not even be the whole of reality. We may be living in just one small corner of a vast and layered structure, a cosmic quilt made of infinite threads. So tonight, let's consider another perspective, the philosophical implications of a multiverse. What does it mean, for example, if you are not the only version of you? If there are other yous in other realities, each living out different versions of your life? At first glance, this idea can feel unsettling. It challenges our sense of uniqueness and identity. If there are infinite copies of you, are you really you? But on closer thought, this perspective can also be strangely liberating. You see, in a multiverse, no single moment defines everything. Every choice you didn't make still unfolds somewhere. Every road not taken becomes a path in another world. There's a version of you that followed your dream, another that made a different mistake, or avoided one altogether. The multiverse doesn't erase meaning, it expands it. Every moment becomes a branching point, a seed for infinite possibilities. Of course, in this universe, the one you're in now, your choices still matter. This version of reality is the one you experience. The others may exist, but they are inaccessible to you. That gives this life a kind of quiet importance. Among all the possibilities, this is the one you're living. This is the version of the universe where you're listening to this right now. And that matters. Now let's return to the science. There's another form of multiverse that we haven't yet explored, and it comes not from cosmology or quantum physics, but from mathematics itself. This is the mathematical universe hypothesis, most famously proposed by physicist Max Tegmark. It starts with a simple observation. The physical laws of our universe are deeply mathematical. From the orbits of planets to the behavior of subatomic particles, nature follows equations. So the question arises, what is it that makes one mathematical structure real and another not? Tegmark proposes a bold answer. They're all real. Every mathematically consistent structure exists, not just as abstract ideas, but as real universes. If a universe can be described by a coherent set of mathematical rules, it exists somewhere in the multiverse. This is sometimes called the level or multiverse, the broadest and most abstract of all. In this framework, there are not just universes with different particles or forces, but ones governed by completely different forms of logic and geometry. Some might not have space or time as we understand them. Others may follow mathematical systems we haven't even discovered yet. This level of the multiverse is especially challenging to our intuition. It asks us to accept that existence itself is a mathematical concept. In a way, it suggests that the boundary between mathematics and reality doesn't exist. They are the same thing. If that's true, then the multiverse isn't just vast, it's infinite in ways we can barely imagine. Perhaps the reason the multiverse exists is because it must, because existence itself is not a special condition, but simply the natural outcome of every possibility unfolding wherever it can. In the mathematical multiverse model, there is no need for a creator, no privileged universe, no central viewpoint, just mathematics becoming reality. This may sound abstract, but it reflects a long history of scientists discovering that math seems to be baked into the fabric of our universe. The equations that describe gravity, electromagnetism, quantum fields, even the expansion of space, they all seem precise, elegant, and eerily effective. As physicist Eugene Wigner once said, the unreasonable effectiveness of mathematics in the natural sciences is something bordering on the mysterious. But if all mathematical structures exist, then the number of possible universes becomes truly uncountable, and most of them would be radically different from our own. In fact, if you were to randomly pick a mathematical universe from the infinite landscape of possibilities, it would almost certainly be nothing like this one. That makes our universe feel even more special, and perhaps also explains why we perceive it as so orderly. In a sea of chaotic possibilities, only a sliver would be stable enough to support structure, stars, atoms, and life. Let's turn now to a more speculative but increasingly discussed possibility, that the multiverse may be not just out there in space, but also somehow within the nature of consciousness. Some researchers, especially at the intersection of physics and philosophy, have suggested that consciousness might be a key component in defining reality. In certain interpretations of quantum mechanics, particularly the observer effect, it appears that quantum systems remain in a state of probability until they are observed. The moment of observation collapses the wave function, resolving uncertainty into a definite outcome. In the many worlds interpretation, this collapse never happens. All outcomes persist, but your consciousness experiences only one. This raises a question. Is consciousness selecting a path through the multiverse? While still highly speculative, some thinkers suggest that awareness itself might be multidimensional, that it may interface with multiple possible realities in ways we don't yet understand. Others argue that consciousness is purely emergent, an effect of complex physical systems. But even then, the brain may be acting as a filter or translator for a reality that is deeper and more layered than we can perceive. Again, none of this is proven, but it opens the door to profound questions. If consciousness plays a role in defining what is real, and if infinite possibilities exist, then what we perceive as a single world might just be one window into a much larger structure. The universe, in this view, is not a fixed stage, but a living process, continuously shaped by observation, interaction, and interpretation. Now, let's look at a different type of multiverse, one grounded in simulation theory. This idea proposes that what we call the universe might be a kind of sophisticated simulation, a computational construct running on an unimaginable scale. While it may sound like science fiction, this idea has gained some serious attention in philosophical and scientific circles. Philosopher Nick Bostrom formulated what's known as the simulation argument. It suggests that if advanced civilizations can create simulations of entire worlds, and if they have the resources to run many of them, then simulated universes could vastly outnumber the one original physical universe. If that's the case, the odds that we're living in the original become very small. In other words, most conscious beings might exist within simulations, not in a foundational universe. That creates a different kind of multiverse, a layered reality, with base-level universes spawning simulated ones, which may spawn others in turn. In such a model, the number of universes depends not on inflation or quantum branching, but on computation, on the capacity of civilizations to create and run simulations. If a single civilization could run billions or trillions of simulations, each with conscious agents unaware of their nature, then again, we're looking at an overwhelming number of realities. This leads to some strange but serious questions. If we're in a simulation, could there be others? Could multiple simulations be running in parallel, some nearly identical, others wildly different? Could our simulation be connected to others or completely isolated? Some scientists speculate that clues to a simulated universe might be found in the nature of space and time, perhaps in quantization, error correction codes hidden in the equations of string theory, or in limitations like the speed of light or the uncertainty principle. So far, no such evidence has been found, but the search continues. If we accept that simulated universes could exist, whether we are in one or not, then the multiverse again becomes vast. Each simulation is a universe, and depending on the parameters, each one could evolve differently. A single civilization might experiment with different versions of physics, or rerun history with small variations, or create entire fictional realities as complex as our own. The implications of this are staggering. It suggests that the number of universes may not be limited by physics alone, but also by imagination, curiosity, and technological potential. But there's another question hiding here. What defines a universe? So far, we've assumed that a universe is a complete, self-contained realm, with its own space, time, matter, and rules. But in practice, the boundary might be less clear. Is a dream a universe? Is a thought? Is a computer simulation as real as a physical world if it contains conscious experience? As we consider all these layers, inflationary bubbles, quantum branches, brain collisions, mathematical structures, simulations, we begin to see that the multiverse is not a single idea. It's a spectrum of possibilities, each arising from different assumptions, each challenging what we think we know about existence. And in that spectrum, the number of universes grows unimaginably large, maybe infinite, maybe layered across dimensions, maybe stacked like stories in a cosmic library. Some may overlap, others may be sealed away, forever unreachable. So once again, we return to our original question: how many multiverses are there? We've explored 5 or 6 different ways to answer it, and all of them point toward abundance, toward plurality, toward a reality that is not singular and still, but dynamic, layered, and infinitely. The journey of science, so far, has always moved toward greater complexity and greater scale. We've learned that atoms are made of particles, that those particles are fields, that space itself expands, that time may be relative. And now, perhaps, that the universe is not alone. Let your thoughts rest here gently. Imagine the multiverse as a great web, not tangled but intricate, not chaotic but alive with possibilities. In this web, every thread is a universe, every crossing a moment, every light a version of you, wondering, asking, dreaming. And perhaps that's the point. Not to count the multiverses, but to feel their presence, to sense, however dimly, that we are part of something vast, and that within that vastness there is space for everything. Now that we've explored many kinds of multiverses, from cosmic inflation and quantum branching to mathematical structures and simulated realities, let's turn to a deeper question. Could the multiverse help explain some of the biggest mysteries in science? One of those mysteries is the fine-tuning problem. When scientists look at the laws of physics in our universe, they find that many of them seem extraordinarily precise. The strength of gravity, the charge of the electron, the rate of cosmic expansion, all fall within incredibly narrow ranges that allow atoms, stars, chemistry, and life to exist. Change any one of these by even a tiny amount, and our universe might become lifeless or chaotic. This has puzzled physicists for decades. Why should the universe be so precisely balanced? Why do the laws of nature seem perfectly tuned for complexity and life? There are a few possible explanations. One is that there's a deeper theory, still undiscovered, in which these values are not arbitrary, but necessary. Another is that they are the way they are by sheer coincidence. But the third possibility is perhaps the most intriguing, that we live in one universe among many, and each universe has its own set of physical laws. In that case, we just happen to be in one of the rare universes where conditions allow life, not because ours is special, but because in all the other ones, no one is there to ask the question. This is called the anthropic multiverse, and while it may not feel like a satisfying answer, it is a powerful one. It transforms the question from why are the laws of physics so perfect to why wouldn't we find ourselves in a universe where the laws allow beings like us to exist? It's a subtle shift in thinking, but a profound one. It invites us to stop treating our universe as the only reference point, and instead see it as one expression among countless others. That perspective may be key to solving some of the puzzles that have long haunted science. Another place the multiverse may offer insight is in dark matter and dark energy, two of the biggest unknowns in modern cosmology. Dark matter is a mysterious substance that doesn't emit light or energy, but seems to make up about 27% of the universe. Dark energy, even stranger, appears to be driving the accelerated expansion of space and accounts for roughly 68% of the universe's energy. That means that everything we can see, stars, galaxies, gas, dust, makes up less than 5% of what's actually out there. We don't yet know what dark matter or dark energy are made of, but some physicists have speculated that their existence may be influenced by the structure of the multiverse. In certain inflationary models, different regions of the universe, or different universes altogether, may have different values for dark energy. Most of those values would lead to rapid collapse or runaway expansion. But in a small fraction of universes, the balance might be just right to allow galaxies to form and life to emerge. In other words, the multiverse might not just explain why our universe works, it might help explain why it exists at all. But this raises another question. If these other universes exist, how do they begin? Where do they come from? To answer that, let's go back to the idea of quantum fluctuations in a vacuum. In quantum field theory, even empty space isn't truly empty. It's filled with energy and virtual particles that constantly pop in and out of existence. These fluctuations are random but inevitable, and in certain conditions, they might give rise to entire universes. Imagine a vast, high-energy vacuum, what physicists call a false vacuum. In rare moments, this vacuum might decay, releasing energy in a burst that sparks the birth of a new universe. That new universe then undergoes inflation, cools, and evolves, just like ours did. This is the mechanism behind many inflationary multiverse models, universes arising spontaneously from quantum events. It's a bit like seeds sprouting in a boundless field. Each sprout grows into its own self-contained world. The field is the multiverse. The sprouts are individual universes, and they never touch. Each is sealed off from the others by the rapidly expanding space around them. This idea may sound wild, but it's grounded in physics. In fact, it's considered by many to be a natural consequence of inflation theory. If our best cosmological models are correct, then it's very likely that universe creation is not a rare event, it's the norm. Now let's consider something even more mind-bending. Could universes create other universes? In some theories, yes. Black holes, for example, might serve as gateways to new regions of space, or even to brand new universes. When a star collapses into a black hole, it forms a singularity, a point where gravity is so intense that space and time break down. But some models suggest that this collapse might bounce into a new expansion, creating a universe on the other side. If that's true, then our universe might be the offspring of another, and every black hole in our universe could be the seed of a new one. That would make the multiverse not a static landscape, but a growing, branching tree, a cosmic genealogy of worlds. This idea is known as cosmological natural selection, proposed by physicist Lee Smolin. He speculates that universes with physical laws that favor black hole formation might produce more offspring universes, leading to a kind of evolution across the multiverse. Over time, universes would select for properties that make more black holes, and thus more universes. It's a radical idea, but it connects two of the most mysterious objects in physics, black holes and universes, into a single story. And it paints a picture of reality as something alive, dynamic, and ever replicating. As we continue to explore, it's worth noting how recent all these ideas are. Just a century ago, we didn't even know the universe was expanding. We had no concept of dark matter, or extra dimensions, or quantum foam. The multiverse, once the stuff of philosophical speculation, has now become a serious topic in theoretical physics. That doesn't mean it's proven. Far from it. But it's being taken seriously, not because it's imaginative, but because it emerges naturally from our best theories. The multiverse is not something we invented to make the universe more exciting. It's something that keeps appearing when we try to understand the universe more deeply. And yet, for all its theoretical support, the multiverse remains elusive. We may never be able to prove it directly. We may never detect another universe, or travel beyond the boundaries of our own. But as we've seen, that doesn't make the idea meaningless. It changes how we frame the questions. It shifts the way we think about origin, purpose, and existence. So how many multiverses are there? If inflation is correct, there may be an infinite number of bubble universes. If the many worlds interpretation holds, there are infinite branches, splitting every moment. If string theory is right, there may be 500 different possible universes. If all mathematical structures exist, the number becomes not just infinite, but limitless in kind. And if simulations are part of reality, then the number may be increasing, constantly, with every act of creation. Whatever the truth, we are part of something vast, perhaps infinitely vast. And whether that vastness is filled with other versions of you, or with strange and alien laws, or with unimaginable forms of structure, it tells us something profound about what it means to exist. So as you rest your thoughts tonight on the edge of this deep question, let the enormity of it settle gently in your mind. You are here, in one thread of reality, one version, one expression of a deeper fabric. And that, in itself, is a miracle of complexity. As we drift deeper into the multiverse, let's pause and reflect on the concept of dimensions. Not just the familiar ones of space and time, but higher dimensions that may be necessary for certain multiverse models to work. These extra dimensions are not just theoretical curiosities. In many frameworks, they are essential scaffolding on which the structure of reality is built. In string theory, for example, the universe is thought to have 10 or 11 dimensions. But why don't we see them? The answer lies in something called compactification. According to the theory, these extra dimensions are curled up so tightly on scales smaller than atoms that they're effectively invisible to us. Like a garden hose seen from far away, the extra dimensions look like one-dimensional lines, even though they contain additional circular dimensions wrapped around them. Now imagine that each way of wrapping or folding these dimensions creates a different universe, with its own particles, forces, and fundamental constants. These aren't just different locations within a single universe. They are entirely separate realities, defined by the deep geometry of space-time itself. This is how the so-called string landscape arises, a vast collection of possible universes, each arising from a different compactification of higher dimensions. The number of such configurations is mind-boggling, possibly as high as 10 to the 500. If you tried to count them, even assigning one per atom in the visible universe wouldn't come close. So instead of asking, why does our universe have the properties it does, string theory suggests we might ask, which compactification of higher dimensions leads to a universe like ours? We may be just one of a huge set of outcomes, but here's something even stranger. The very vacuum of space may differ between universes. What we think of as empty isn't really empty at all. It has a specific energy level, the vacuum energy, and this energy determines whether a universe expands rapidly, stays stable, or collapses. In our universe, the vacuum energy is very small, but not zero. That tiny value allows stars, galaxies, and life to form. If it were just a little larger, the universe would have expanded too fast. If it were negative, space would collapse. In a multiverse, universes with different vacuum energies may fill the landscape, but only the rare few with just the right balance can support observers. Again, this feeds into the anthropic explanation. The reason we observe a universe so finely balanced is because only such a universe can be observed. Let's move away from the abstract and consider something a bit more grounded: patterns in nature. From snowflakes to galaxies, reality seems to be structured by recurring forms: spirals, fractals, symmetry, and order. Some physicists wonder whether these patterns reflect deeper laws that might be universal, even across different universes. Could there be certain constants, not of physics, but of structure, that appear in many types of realities? Could logic itself be a kind of thread connecting all possible worlds? If so, that might suggest that even if universes differ wildly in content, there may be meta-laws, higher-order rules that govern the structure of reality in general. These wouldn't determine the details of each universe, but would define the space of possibility itself. This leads to an intriguing idea. Perhaps the multiverse isn't a chaotic jumble of unrelated worlds, but a kind of cosmic ecology, with structure, relations, and evolution. Not unlike a forest, where each tree is distinct but part of a larger system. If true, it would mean the multiverse isn't just big, it's organized. And that organization might someday be discoverable. Even if we can never travel between universes or even see them, we might be able to infer their existence and properties from the patterns they leave in our theories. So how might we do that? One promising direction is through cosmic background radiation, the relic light from the early universe. Some multiverse theories suggest that if our universe collided with another in its early moments, it might have left a faint circular imprint in the microwave background, a kind of bruise from an ancient encounter. So far, no such signature has been confirmed, but the search continues. Another possible clue might come from gravitational waves, ripples in space-time caused by massive events like black hole mergers. If universes collide or form from the decay of a higher energy vacuum, they might release gravitational energy that leaves behind a faint but detectable signal. Future detectors, far more sensitive than the ones we have now, may be able to pick up these whispers from beyond. Still, the biggest clues may come not from direct observation, but from consistency. If multiple independent theories all point toward the existence of other universes, even in different ways, then that convergence becomes compelling, and we're already starting to see that. Quantum mechanics, inflation, string theory, and even information theory all seem to suggest that reality is deeper than it appears. Each comes from a different angle, but they point toward the same horizon, that the universe is not singular, that there are more. As we drift further into these ideas, let's revisit something that may be easy to overlook. What does it mean to exist in a multiverse? In a traditional sense, existence means being real, present, tangible. But in a multiverse, that definition changes. Reality becomes relative, not because it's uncertain, but because it's layered. What's real for you might be completely inaccessible to someone in another universe, and vice versa. In this view, context becomes everything. You exist within your own universe's rules, and so does everything else. There's no absolute center to reality, only a vast plurality of experiences, each valid within its own framework. That's a deeply humbling realization. It dissolves the idea of a single objective reality and replaces it with something more like a mosaic, a tapestry of overlapping, non-conflicting truths. Each universe is a perspective, and together they form the totality of existence. So once again, how many multiverses are there? It depends on the framework. According to eternal inflation, infinite. According to quantum theory, branching endlessly. According to string theory, 10, 500 or more. According to mathematical realism, every logically possible structure. And according to simulation theory, perhaps millions or billions, limited only by computational creativity. Each model offers a different answer, but all of them agree on one point, more than one. Perhaps that is the true lesson of the multiverse, not to know the number, but to understand the principle, that reality, in its deepest sense, may be inherently multiple, that diversity is not just a feature of life, but of existence itself. And in that vastness we find something beautiful, the recognition that our universe, as grand and complex as it is, might be just one note in an infinite cosmic chord, one ripple in an endless sea. Let that idea rest with you tonight, not as a burden, but as an invitation to curiosity, to awe, and to the quiet possibility that there is always more. As we continue this journey through the concept of the multiverse, we come to a strange and delicate question. Does the multiverse have a beginning, or is it eternal? To answer that, we need to look at the origins of our own universe first, the Big Bang. The Big Bang is often thought of as the beginning of everything: time, space, energy, and matter. But many physicists now believe that the Big Bang was not necessarily the beginning of all reality, just the beginning of our observable universe. In inflationary cosmology, the Big Bang may have been a local event, the sudden heating and expansion of a small patch of space that had previously been inflating. In this view, other regions of space may have also undergone similar events, either before, after, or at the same time. That means the multiverse could precede the Big Bang, or even have no beginning at all. This leads us to the idea of an eternal multiverse, a system that has always existed in some form, constantly generating new universes through fluctuations, inflation, or quantum processes. No singular moment created it. No final moment will end it. It simply is. Timeless, dynamic, always expanding, always unfolding. But how can anything exist without a beginning? It's difficult to imagine because our minds are shaped by time. Everything we experience has a before and an after. Every event has a cause. But in physics, especially in cosmology, time itself may not be a universal feature. It might emerge only under certain conditions, like the cooling of space or the formation of matter. Some theories propose that time is not fundamental, that before the Big Bang there was no before because time didn't exist yet. Others suggest that time may run differently in different parts of the multiverse. Some universes may experience time as we do, Others may have no time at all. Still others might loop, reverse, or run on entirely unfamiliar timelines. In such a model, the multiverse becomes a kind of timeless structure, or perhaps an ever-evolving process beyond time. We may never know which is true, but asking the question forces us to rethink everything we assume about causality and origins. Now, let's take a moment to revisit a concept we touched on earlier, the many worlds interpretation of quantum mechanics. But this time from a different perspective. Imagine you're faced with a decision. You can go left or right. You choose right. In the classical view, the left path is gone. It didn't happen. But in the many worlds view, both outcomes happen. There's a version of you who turned left and one who turned right. Each version continues, unaware of the other. The universe has branched. Now multiply this idea by every quantum event, every particle interaction, every choice, every fluctuation, and you get a constantly branching multiverse, growing at every moment. In this model, time doesn't just move forward. It branches outward like a tree growing infinite limbs in every direction. This creates not just parallel universes, but a continuously multiplying structure of realities, each slightly different from the others, each evolving according to its own sequence of events. But here's where it gets really interesting. Some physicists suggest that these branching universes may not just exist alongside each other, but may interfere in subtle ways. In quantum experiments, particles sometimes behave as if they are affected by other possibilities, ones that didn't occur in our observed outcome. This leads to the speculation that different branches might be mathematically entangled, even if they're physically isolated. It's as if all the universes are part of one giant quantum structure, with interference patterns and hidden connections. In this view, the multiverse isn't a collection of separate worlds, but a single vast quantum state, with our reality being one thin slice through that state. We don't yet know if this is true, but it reveals the extraordinary richness of quantum theory and its potential to describe a reality far beyond what we can see. Now let's shift from physics to something more personal, something closer to the heart. In a multiverse where all possible versions of you exist somewhere, what becomes of identity? Are you just one of the many? Are you defined by your choices, your memories, your timeline? Or are you as part of something broader? A network of selves, each living out a different version of what could be. This idea can be unsettling, but it can also be comforting. It suggests that no experience is wasted, that somewhere every potential within you has been explored. Every version of your life has meaning, even the ones you didn't live. And it reminds us that what we do here, in this version of reality, still matters deeply. This is the version you're aware of. This is the universe you're living in. Your experiences, your thoughts, your feelings. They are not diminished by the existence of others. They are enriched by it. Because in this moment, in this branch, you are the only you there is. And that makes this universe, your universe, uniquely precious. Let's now consider one final possibility. What if all these models, inflationary, quantum, string theory, simulation, mathematical, are not mutually exclusive? What if multiple kinds of multiverses exist together? Some physicists have proposed that reality might be layered, with different kinds of multiverses stacked on top of one another. An inflationary multiverse that spawns different universes with different constants. Within each of those, quantum branching produces even more versions, and within some of those, simulations are run, creating even more layered realities. It's like a hall of mirrors reflecting endlessly, not just copies, but kinds, categories of universes, each with its own rules of formation, its own scope, and its own inner logic. This would make the number of multiverses not just large, but hierarchical, structured like a cosmic taxonomy of existence. In that case, the question, how many multiverses are there, becomes not just a matter of counting, but of mapping, understanding the architecture of all that is, from the most basic to the most complex. We may never be able to count them, but we may be able to model them, to build mathematical frameworks that help us describe their relationships, their boundaries, and their interactions. This would be the next frontier of physics and of philosophy. Because ultimately, the multiverse is not just a scientific idea. It is a mirror of imagination, a projection of what we believe is possible. It challenges the limits of observation, of theory, of understanding. But it also inspires. It calls us to think bigger, to stretch beyond what's familiar, and to embrace uncertainty not as a flaw, but as a feature of reality. At this point in our journey through the multiverse, we've explored many branches of theory, each pointing toward the possibility that our universe is just one of many. We've followed inflationary bubbles, quantum splits, string theory landscapes, mathematical structures, simulations, and more. But before we begin to close the loop on this cosmic thought experiment, let's ask something even deeper. If multiverses exist, can they interact? In most models, the answer is no. Universes are typically sealed off from each other by causal separation, by dimensional barriers, or by quantum decoherence. But in some theories, limited interaction may be possible, at least in very rare or subtle ways. For example, in brain cosmology, which emerges from string theory, our universe could be a three-dimensional brain floating in a higher dimensional space. Other brains, other universes, could exist parallel to ours, just slightly offset in dimensions we can't perceive. Occasionally, these brains might collide, an event that could potentially create a Big Bang. In this view, the origin of our universe was not the beginning of everything, but just a collision event in a larger multiversal framework. If such collisions are rare but repeatable, the multiverse becomes a cyclical structure, with universes colliding, rebounding, and evolving again and again. Could we detect such a collision? Maybe. Some scientists have searched for circular anomalies in the cosmic microwave background, faint rings or patterns that might hint at another universe brushing up against ours. Nothing definitive has been found, but the search continues. Another possibility comes from quantum mechanics. If the many worlds interpretation is true, and all possible outcomes of quantum events split into separate universes, could these universes ever recombine? This process is called quantum interference, and it's a key part of what makes quantum computing work. Under very specific conditions, separate branches of quantum outcomes can interfere with one another, producing measurable effects. In ordinary life, decoherence prevents this, but in carefully controlled systems, interference patterns can emerge, offering glimpses of a broader quantum structure. While this doesn't mean entire universes can recombine, it does suggest that quantum-level effects may hint at the deeper fabric of reality, a multiverse that is not just a collection of worlds, but a unified quantum object, complex and interwoven. Now let's take a brief detour into the world of information theory, where some of the most cutting-edge ideas in physics are emerging. Information theory tells us that everything physical, particles, forces, even space and time, may be emergent from information. In this view, the universe is not made of things, but of bits, zeros and ones, quantum states, probabilities. If that's true, then different universes may simply be different configurations of information, just like different files on a computer. That's where digital physics comes in. the idea that the universe is fundamentally computational, that space and time arise from discrete units of information processed by a kind of cosmic code. From this perspective, multiverses could be computational branches, each evolving from different starting conditions, each running its own unique version of the code. And in that case, the number of multiverses becomes a matter of computation. How many ways can information be arranged and run? It's not just speculative. Some physicists have found error-correcting codes embedded in the math of string theory, the same kind of codes used in digital communication. That's led to speculation that reality may be self-correcting, like a computer system that keeps itself stable by detecting and repairing errors. If that's true, then each universe might be not only distinct, but self-contained, resilient, and optimized, like a perfectly tuned algorithm running in a cosmic processor. And that makes us wonder who or what is running the program. This takes us back to simulation theory, but also deeper to the question of emergence. Perhaps no one is running the program. Perhaps the universe is the program, a self-generating system with no outside observer. Still, the resemblance to computation, the structured, logical, layered behavior of the universe, suggests that even if we are not in a traditional simulation, we may be part of a computational multiverse. Let's step back now and imagine all the types of multiverses we've encountered so far. The inflationary multiverse, with infinite bubble universes forming from space inflation. The quantum multiverse, with every possibility realized through branching realities. The brain multiverse, with parallel universes floating in higher dimensions. The cyclic multiverse, where universes are born from the death or collision of others. The mathematical multiverse, where all logically possible structures exist. The simulated multiverse, where civilizations create new worlds in digital realms. The computational multiverse, where information itself defines what is real. Each model arises from different principles. Each answers different questions. But together, they form a vast, overlapping picture, not of a single idea, but of layers of reality. So why does this matter? Because the multiverse forces us to expand our thinking, to imagine that our universe, as immense and complex as it is, might be just one expression of reality. It challenges the idea that there's one truth, one path, one framework. It invites us to consider plurality, not just in science, but in philosophy, in meaning, in experience. And it humbles us. Just as the discovery that Earth was not the center of the cosmos changed our perspective, so too does the multiverse. It shows us that we may never see the whole picture, that what we observe is just one window, one frame, one patch in a much larger fabric. But that doesn't make our patch any less important. On the contrary, it reminds us that every version of reality matters. Every thread in the tapestry has its role. And by exploring our corner of existence with curiosity, with care, and with awe, we connect to something greater. Let your mind rest in that idea for a moment. The multiverse is not a place we can visit. It is not a destination. It is a framework, a way of thinking that stretches the imagination and redefines the boundaries of what's possible. And within that infinite landscape, you are here, conscious, wondering, listening. You are not lost in the multiverse. You are part of it. The truth is, we may never know. Not because we aren't clever enough to figure it out, but because some questions don't have final answers. They stretch us, not to be solved, but to be contemplated. Like the horizon, always just out of reach, always inviting us to keep walking, keep asking. What we can say is this: the idea of the multiverse is not science fiction anymore. It is a serious, growing part of physics and cosmology. Not because scientists want it to be true, but because it's where the evidence, the mathematics, and the logic seem to lead. Different theories offer different numbers. Some say infinite, others suggest specific figures, 10 or 500 or more or less. Some multiverses branch constantly, others expand like bubbles. Some are purely mathematical, others may be simulated. Each version is a lens, helping us to see our own universe more clearly. But the most important realization may be this: we are not the center of everything, and yet we are not insignificant. The multiverse, if it exists, is not here to diminish us. It's here to deepen us. It tells us that existence is bigger than we thought, that life is rarer and more precious than we imagined, that this moment, right here, in this version of the universe, in this quiet thread of time, is something to hold with wonder. Because no matter how many universes exist, one, many, or infinite, this one is yours. In all the swirling potential of everything that could be, this is the version of reality where you are lying down, listening, breathing, existing, and that is a miracle. Maybe somewhere there's a universe where none of this happened. No planets, no stars, no listeners. But here, tonight, there is light, there is sound, there is thought, there is you. So let the multiverse drift now into the background of your awareness, not vanished, but resting like the stars behind clouds. You don't have to solve it, you don't have to reach its edge, just knowing that it might be there is enough. Let your mind grow quiet now. Let curiosity turn to calm. You've traveled far, across space, time, dimension, theory, and imagination. And now it's time to return, not to the answer, but to the gentle mystery that remains. In a universe of infinite possibilities, you've found this one. And for now, that is everything. Good night from SleepSpace.